we have seen that an assembler as such, it can be designed in two passes. Pass 1, pass 2. Single pass assemblers and two pass assemblers. Whatever might be the type of number of passes required, the functionality of the assembly process is similar. We know that as such, an assembler will accept as a program in assembly language, and this has to be translated to the target machine code. How this can be done? This will be done by scanning statement by statement. Each line will be scanned by the assembler. Every statement will be having some particular syntax, and subdividing these units in the statement. Assembler will have to do a lot of housekeeping works to generate the final target code. Now, for this purpose, and assemblers are broadly classified into single pass assembler and two pass assembler. And in single pass assembler, the entire assembly process is done in a single go. In that case, we have seen that when the assembler scans through the input, there will be moments where a final action could not be taken. In that case, backpatching technique will be applied. Assembler will come back again, and wherever there are unfilled informations, those information will be added later. In two-pass assembler, there is an analysis and synthesis part. In the analysis part, each of the statements will be scanned. In fact, assembler will subdivide the entire statement into a lot of sections. Each section in a state will be having separate meaning. Like the statement we have seen earlier, John start 0. There, John is the name of the program. Start is a pseudo opcode that tells the assembler that the instruction that followed belongs to a program called John, and 0 indicates the starting value of the location counter. These three things are to be rightly interpreted by the assembler. In that case, it will have to separate the symbols, it will have to separate the opcodes. They can be either pseudo opcodes or machine opcodes. Every opcode can have either 0 or more operands, so each of the operands fields will have to be separately considered. And since we have learned about assembly language programming, we also know that position of the portions of an assembly language statement is also having a meaning. There will be several fields in the assembly language program, so all these fields will have to be identified. Then symbol table will have to be created. LC value will have to be properly incremented. Then the information in pass 1 and intermediate representation will be created. This will be passed to the pass 2 of the assembler, in which the entire synthesis part will go on, and after pass 2 we will get the real target code. To achieve this entire thing, now let us look into design of a two-pass assembler. And for this purpose, assembler will require a lot of databases. Machine operation table, pseudo operation table, symbol table, base table, and literal table. These are the databases required in the assembly process. And we have seen what is meant by MOT, and also we have seen what is what meant by POT. The common thing between these two tables are they are fixed tables that describe about the machine opcodes and pseudo opcodes respectively. Information kept in these two tables are different. In the case of machine opcodes, each machine instruction is binary opcode. Length of a machine opcode instruction is instruction format. These things will be kept. And once it is there, it is not going to be updated in the assembly process. It is done, created before the hand for a particular assembly language. Similarly, in the pseudo operation table, each pseudo opcode and actions to be performed for each pseudo instruction. What's to be done when start is there? Similarly, there are other pseudo code opcode instructions. For each opcode instruction, what is the action to be performed? This fact will be stored in POT. Symbol table is a data structure which is used to store the details of all symbols used. What do you mean by symbols? It can be name of variables. So name of a symbol will have to be stored. Its location in main memory is to be calculated. It is to be stored. Its length, everything in hexadecimal, and whether the address is relative or absolute. When we say that the value is absolute, whatever value the assembler assigns at the time of assembly process, that address will be used when the program is getting executed also. That means assembler will have a clear idea about the location of the program that will be allocated to it in the primary memory for this particular program. There are instances like that. In some cases, it will be relative. Now, since we know about the concept of a process, we know that whenever we say a dot out in the background, what is a dot out? A dot or out, we will say this is command to after compiling our CPP program. Then we say a dot out. What is a dot out? A dot out is the executable code for our program, and a dot out will be continuously overwritten whenever we compile a program. Say I wrote my factorial program in CPP, I compiled that. Now a dot out will have the executable code for finding my factorial. Later I do a different program, do GCC, a dot out will be changing. So now I say a dot out. In that case, in the background, a process will be created. My source code, which resides in a dot out, will be transferred to primary memory, and the real execution happens. There is an invisible loader that do all these things when we say a dot out. Invisible in the sense it is invisible for the user as such. Now we know that whenever a process is allocated, a process can be blocked. There is a blocked state. And when we say a process is getting blocked, it can be even suspended also, whatever it might be. When a program is getting blocked, that program will be no longer in the running state. In that case, instead of our process, there is every chance that the OS can adopt or accept a new process, and new process can start. In that case, suppose that the primary memory is not enough to load this new process. In that case, OS will take a decision regarding shuttling our block program in the primary memory to an area called as swap area in the secondary storage device. When this swapping occurs, our block program is temporarily moved to the secondary storage area, and the primary memory occupied by the block process is now free to be allocated for other process. That gives us enough indication regarding the address is absolute or relative. In that cases, a relative mode will be more apt because when the process is given a second chance for running after the blocked state, there is no guarantee that the program will be still running with the same block of memory. Program may be allocated a different block of memory where there is a different range of addresses. Then also the program will have to resume. The keyword is resuming, not restarting, because when the process is getting blocked, it has to restart from where it was blocked. So to make it happen, process will be maybe allocated a different block of memory, still the process has to run. In that case, relative mode will be more apt. Anyway, what is the address stored in for a symbol, and whether that symbol address is either relative or absolute, even these facts will be stored in the symbol table. And please note that many of these fields will be filled in pass 1 and in pass 2 as well. Many informations will not be available for in pass 1. In that case, unfilled fields will be kept unfilled and it will be filled later in the symbol table. Next table is literal table. Now, what is a literal? What is a constant? What is a symbol in assembly language? This is a topic of interest for you, and I hope that you might have learned about this. I had even shared a reference link in the Google Classroom 2 days back. I hope you have seen that. There you can see a good discussion on literals. Now, literal table is used to store literals in the source assembly language code. What are literals? Literals are used to define constants without a name. It can be a numeric, string, boolean, or a single character. And you can see the fields in the literal table. You have the symbol as such, then the location, address, length of the symbol, and whether it is relative or absolute, and what is the usage for that. Is it a literal? And what's the actual value that is represented by that literal? So these things will be filled in the literal table. See, the exact, we know that assembly language varies from assembler to assembler. So for the sake of illustration, we have taken an IBM 360 assembler where there is instruction called as CR5 equal to F16. This is an instruction for comparing the value of a register against a value, a constant. So here you can see that R5 is register 5 and this entire part is a literal. This specifies that the value is 16. So in this case, this portion is called as a literal. So here, assembler has to translate this literal as a word with its value 16. So there can be constants that represents a literal and what is the length of a literal. So all these things will have to be extracted from the source program by the assembler and it will have to be added in the literal table for the sake of generating target code. Last table is base table. In the base table, address of a symbol relative to the beginning of the program will be stored. What do you mean by the relative to beginning of a program? Suppose that we keep the base address. See, we have a start 0. John start 0. In our early illustration, we have seen such a pseudo opcode. That means the value of location counter is set to 0. So relative to the base address, to the starting address, what is the position of a literal? So when we calculate in that way, even if the base address changes, easily the other addresses can be calculated. Suppose that initially we start say with a temporary address called as say 0FFF and corresponding to FF where the symbol X is stored. Say it might be some 16 bytes, there can be a difference of 16 bytes for the base address. So in that case, this base table will give enough information to generate the code for finding the exact address for each symbols in the program, and the address of all symbols will be listed in the base table relative to the beginning address of the program.